Hi students, in this video I am going to talk about multinomial distribution and convolution formula for PDF of sum of independent random variables and probability distributions of transformations in RK. Okay, let me get started with multinomial distribution. One of the most important multivariate distribution is multinomial distribution, which often arises when we consider sequence of independent identical experiments which result in k possible outcomes, which is a generalization of binomial distribution, where binomial distribution arises when we consider sequence of independent identical Bernoulli trials. Bernoulli trials are experiments which result in two possible outcomes, success, failure. Here experiment result in k possible outcomes. Okay, fine. Now let us denote the k possible outcomes of the experiment as R1, R2, so on Rk with respect to probabilities P1, P2, Pk, where the sum of the Pi's from 1 to k must be equal to 1 because experiment must result in one of the R1, R2, Rk. Okay. Here we are performing sequence of n independent identical experiment of above kind in the sample space omega consisting of outcomes which are sequence of x1, x2, xn of length n, where each xi is one of R1, R2, Rk for I equal to 1 to n. Okay, this is going to be our sample space. Okay, for non-negative ni's for which summation ni from 1 to k equal to n, we can define this event En1, N2, Nk, which consisting of outcomes omega in capital Omega, in which N1 R1s, N2 R2, so on Nk Rks. Okay, all such an outcomes are sitting in this event En1, N2, Nk. Okay, from combinatorics we can see that the number of elements in En1, N2, Nk going to be n factorial by n1 factorial, n2 factorial, so on Nk factorial. Okay. For any outcome in En1, N2, Nk, the probability of singleton omega going to be P1 to the power of N1, P2 to the power of N2, so on, Pk to the power of Nk because of independence. What is Pi? The probability of experiment result in Ri. Okay. We had similar discussions in a binomial case. Okay. Same argument. So that's why the probability of the singleton omega going to be P1 power N1, P2 power N2, so on, Pk power Nk because of independence. Fine. Okay. Let xi denote the number of Ris in n trials for I equal to 1 to k. Now we have a k-dimensional random vector x under bar, which is a vector of x1, x2, so on, xk. Okay, which support Sx under bar, which consisting of non-negative integer solutions of this equation. Okay. Now let us look at the joint PMF of x under bar. The Px under bar at n1, n2, nk is going to be, by definition, the probability of x1 equal to n1, x2 equal to n2, so on, xk equal to nk. Okay, this event happen if and only if outcome come from this event en1, n2, nk. Okay, that's why the probability of this event equal to probability of en1, n2, so on, nk. Okay, now the probability of En1, N2, Nk we can write sum of probability of the singleton omega where omega runs over En1, N2, so on, Nk. Okay, and we already know probability of each singleton omega from En1, N2, Nk is P1 to the power of N1, P2 to the power of N2, so on, Pk to the power of Nk. Okay. So we have the summation of P1 to the power of N1, P2 to the power of N2, so on, Pk to the power of Nk, where sum runs over En1, N2, so on, Nk. Okay. So this is common to each term. So if I take this one common, so we have a sum of these ones where sum runs over En1, N2, so on, Nk. Okay. So this sum is going to be equal to size of this set En1, N2, Nk, which is n factorial by n1 factorial, n2 factorial, so on, nk factorial. Okay. Now, and we can recognize this one as multinomial coefficient. So using multinomial coefficient notation, we can write the px under bar at n1, n2, nk going to be n choose n1, n2, nk, p1 to the power of n1, p2 to the power of n2, pk to the power of nk. This is the joint PMF of x under bar at n1, n2, so on, nk. Okay. Now let us check the validity of this joint PMF. Okay. First of all, it is easy to see that it is a non-negative function. Okay. And the total joint PMF values over the support is going to be equal to 1 because of multinomial theorem. Okay. This is going to be exactly equal to multinomial expansion of P1 plus P2 plus so on Pk power n. So that's why. So this sum of the joint PMF values or support we can write P1 plus P2 plus Pk over to the power of n. But we know the sum of Pi is from 1 to k equal to 1. This is nothing but 1 to the power of n, that is 1. Okay. So total joint PMF values over the support equal to 1. So it's going to be valid joint PMF. Fine. Okay. This is a notation. We read it as this x under bar follows multinomial distribution with a parameter n vector p1, p2, pk. Okay, fine. Okay. Next note, this binomial distribution is going to be special case of multinomial distribution. This binomial distribution with the parameters n comma p same as multinomial distribution with the parameters n comma vector p1, p2, where p1 is p, p2 is 1 minus p. Okay, fine. Here is the example. Let us say we have a die whose probabilities of landing on outcomes 1, 2, 3, 4, 5, 6 respectively are 1 by 5, 3 by 10, 1 by 5, 1 by 10, 1 by 20, 3 by 20. Okay. Here our experiment result in 6 possible outcomes. Okay. This is going to be our R1, R2, so on. This is R6. Okay. R1 is 1, R2 is 2, R3 is 3, so on. R6 is 6. Okay, the respective probability, this is a P1, P2, so on, this is P6. Okay, and if you roll a die 9 times, here n equal to 9. Okay, here n is 9. Then find the probability that 1 appeared 3 times, 2 and 3 appeared twice, and 4 and 5 once each, 6 not at all. Okay, now let's solve this problem. Here let xi denote the number of i's in 9 trials for I equal to 1 to 6. Then this random vector x1, x2, x6 follows multinomial distribution with the parameters 9 and vector of probabilities 1 by 5, 3 by 10, 1 by 5, 1 by 10, 1 by 20 and 3 by 20. Okay, this is the P1, P2, P3, P4, P5, P6 and small n equal to 9. Okay, fine. Now here we are interested in the probability of x1 equal to 3, x2 equal to 2, x3 equal to 2, x4 equal to 1, x5 equal to 1 and x6 equal to 0. That means the joint PMF value at 3 comma 2 comma 2 comma 1 comma 1 comma 0. Now, using the joint PMF of multinomial distribution with the parameters 9 and the vector of probabilities 1 by 5, 3 by 10, 1 by 5, 1 by 10, 1 by 20, 3 by 20, the probability of this event is going to be this one. Okay, so this whole thing gets simplified to 0.00217728. Okay, so feel free to verify this. Okay, so this is how we use multinomial distribution. Fine. Distribution of sum of two independent random variables. Okay, suppose x and y are independent continuous random variables with a PDFs fx and fy respectively. Then we want to find the PDF of x plus y. For that, first let us consider CDF of x plus y. Then we can differentiate it to get the PDF of x plus y. Okay. Now let us consider the CDF of x plus y. CDF of x plus y at t, by definition it should be probability of x plus y less than or equal to t. To get the probability of x plus y less than or equal to t, we have to double integrate joint PDF over the region x plus y less than or equal to t. If this is x plus y equal to t, then x plus y less than or equal to t region going to be this. Okay. Okay. So we have to double integrate the joint PDF of xy over the region x plus y less than or equal to t. This is how we end up with probability of x plus y less than or equal to t. Fine. Here x and y are independent, right? So the joint PDF is going to be product of its marginal PDF fx of x times fy of y. Fine. Now if I integrate first with respect to x, then with respect to y, then x limit is going to be minus infinity to here x equal to t minus y. Okay, x limit is going to be from minus infinity to t minus y, and y limit is going to be from minus infinity to infinity. Okay, now if I replace the joint PDF with product of its marginal PDFs, and here x limits are minus infinity to t minus y, and y limits are from minus infinity to infinity. Okay, now first we are integrating with respect to x, so we can get fy of y out of the first integral like this. Okay, now this is our integral with respect to x. Okay, that's why we can get fy of y out of the first integral, because it's kind of a constant when we are integrating with respect to x. Okay, now because of the relation between pdf and cdf, this can be realized as cdf of x at t minus y. Okay, so I can write this form: integral minus infinity to infinity. The inner integral I can write as cdf value of x at t minus y and fy of y dy. This is the cdf of x plus y at t in terms of cdf of x and pdf of y. Okay, fine. Now we can differentiate CDF of x plus y with respect to t to get the PDF of x plus y. Okay, so to get the PDF of x plus y, we can differentiate CDF of x plus y with respect to t. That means we have to differentiate the same thing right hand side. Now here we can actually perform this differentiation under integral sign because of Leibniz rule. Okay, so you can actually perform this differentiation under integral sign because of Leibniz rule. Here we are differentiating with respect to t. So only this capital Fx is involving t. Okay, so that's why we have to differentiate only this. Okay, if you differentiate the CDF, you will get the PDF, right? So the derivative of fx of t minus 5 with respect to t going to be small fx of t minus 5. So this is what we end up with. Okay, fx plus y of t equal to integral from minus infinity to infinity fx of t minus 5 times fy of y dy. Okay, this integral with respect to y. Okay, this is the convolution formula for PDF of x plus y in terms of PDF of x and PDF of y. Here fx plus y is called convolution of fx and fy. Fine? Okay, next. Let's do a problem here. X and y are independent uniform random variables over interval 0, 1. Then we have to calculate the PDF of x plus y. Here we are going to use convolution formula for PDF of x plus y. Okay, first of all, here x and y are uniform random variables over interval 0, 1. So I can write down the PDF of x like this: fx of x 1 for 0 less than or equal to x less than or equal to 1, 0 otherwise, fy of y 1 for 0 less than or equal to y less than or equal to 1, 0 otherwise. Okay, now the convolution formula that we have for PDF of x plus y is this: fx plus y of t equal to integral minus infinity to infinity fx of t minus y fy of y dy. Let me break this integral into three parts like this: minus infinity to 0 fx of t minus y fy of y dy plus integral 0 to 1 fx of t minus y fy of y dy plus integral 1 to infinity fx of t minus y fy of y dy. Okay, Fine. Now we know that Fi of y is 0 outside interval 0, 1. So from minus infinity to 0, Fi of y value will be 0. So this whole integral will be 0. From 1 to infinity, this Fi of y value will be 0. So this whole integral will be 0. From 0 to 1, this Fi of y equal to 1. So this convolution will be simplified to this integral 0 to 1 fx of t minus y dy. So this is the PDF of x plus y at t. Okay, fine. Now we know that x take the values in the interval 0, 1 and y take the values in the interval 0, 1. So x plus y takes the values in the interval 0 to 2. So as the support of x is 0 to 1 interval, as support of y is 0 to 1 interval. So the support of x plus y going to be interval 0 to 2. Fine. So obviously this fx plus y of t values will be 0 outside interval 0 to 2. Only interest is this fx plus yt value for t in the interval 0 to 2. Fine. Okay. Now, as we can see here, the fx take the value 1 only when we feed something between 0 and 1, otherwise it is 0. So this fx of t minus y value will be 1 only when this t minus y is between 0 and 1. So this fx of t minus y value equal to 1 if and only if this t minus y coming from between 0 and 1, right? Okay. Here fx of t minus y equal to 1 if and only if t minus y come from interval 0 and 1. Okay. Same thing I can rewrite like this. If I multiply with a minus each side, inequality get reversed. So I can write minus 1 less than y minus t less than 0. If I add t each side, I end up with this. T minus 1 less than y less than t. Okay. Fine. So this fx of t minus y equal to 1 if and only if y is between t minus 1 and t. What is the simplified convolution that we have for PDF of x plus y? This one. Fx plus y of t equal to integral 0 to 1 fx of t minus y dy, right? Okay. We already realized that fx plus y of t value 0 when t come from outside interval 0 to 2 as a support of x plus y is interval 0 to 2. Only interest is fx plus y of t value for t in interval 0 to 2. There are two cases here. T may be in the interval 0 to 1 or 1 to 2. Okay. Let us look at case 1. For 0 less than or equal to t less than or equal to 1, that is t is between 0 and 1 like this, then t minus 1 will be less than 0. It will be left side of 0 like this. Okay, fine. First of all, let's break down this integral into two parts like this. Integral 0 to t fx of t minus y dy plus integral t to 1 fx of t minus y dy. Okay. We know that this integrand fx of t minus y equal to 1 if and only if y is between t minus 1 to t, otherwise it is 0. Okay, that means when y from t minus 1 to t, this fx of t minus y value 1, otherwise it is 0. But our interval of integration is 0 to 1. Okay, so from 0 to t, this green portion, the integrand is going to be 1. From t to 1, this black portion, it will be 0. Okay, so here the integrand is going to be 0. So the whole integral will be 0. Okay, and from 0 to t, the integrand value is 1. Okay, so that's why we end up integrating this one integral 0 to t dy, we got t. So for 0 less than or equal to t less than or equal to 1, fx plus y of t value t. Okay, fine. Next, case 2, for 1 less than t less than or equal to 2, that is when t is between 1 and 2 like this, t minus 1 will be between 0 and 1 like this. Here is the t minus 1. Okay, and we know that this integrand fx of t minus y equal to 1 if and only if y is between t minus 1 to t, that is this, in this range, right? And our interval of integration is 0 to 1. Okay, so if I break this integral into two parts like this, integral 0 to t minus 1 fx of t minus y dy plus integral t minus 1 to 1 fx of t minus y dy. Okay, now as you can see in this green portion, t minus 1 to 1, the integrand value 1. Okay, in this black portion 0 to t minus 1, the integrand value will be 0. So this integral will be 0 and this will be t minus 1 to 1 dy. Okay, that's why we end up integrating integral t minus 1 to 1 dy, that will be equal to 2 minus t. So for 1 less than t less than or equal to 2, fx plus y of t equal to 2 minus t. Fine. So we have the PDF of x plus y at t, fx plus y of t equal to t for 0 less than or equal to t less than or equal to 1, 2 minus t for 1 less than t less than or equal to 2, 0 otherwise. Okay, if you look at the sketch of this PDF, it looks like a triangular shape. Because of the shape of the PDF of x plus y, this x plus y is said to have something called triangular distribution. Fine. Okay, next. Now we are going to get the convolution formula for PMF of sum of two independent discrete random variables. Okay, suppose x and y are independent discrete random variables with the PMFs px, py respectively. Then PMF of x plus y, by definition, the px plus y of t should be probability of x plus y equal to t. Now this event x plus y equal to t can be expressed as union of these events x equal to x, y equal to t minus x, where this union runs over x belongs to support of x. Because if x take the value x, y must take the value t minus x, so that x plus y value equal to t. Fine? Okay. Now these events are mutually exclusive. So by finite additivity or countable additivity, this probability of union we can write sum of the probabilities like this. Okay? Fine. Now this is actually joint PMF value at x comma t minus x. So let's write that. So this summation we can write summation of pxy of x comma t minus x, where the sum runs over x belongs to support of x. Now here x and y are independent random variables, so the joint PMF must be product of marginal PMF. So this pxy of x comma t minus x value we can write this px of x times py of t minus x, since x and y are independent. Okay, this is the convolution formula for PMF of x plus y in terms of PMF of x and PMF of y. Here, this px plus y is called convolution of px comma py. Fine? Okay. We already know that sum of independent binomial random variables with the same probability of success again binomial. Now let us verify the same fact using the convolution formula. Okay. Let x and y are independent and x follows binomial distribution with the parameters m comma p, y follows binomial distribution with the parameters n comma p. So the support of x going to be 0, 1, 2, so on m. Support of y going to be 0, 1, 2, so on n. Okay, if x can take the value from 0 to m, y can take the value from 0 to n, then x plus y can take the value from 0 to m plus n, right? So the support of x plus y going to be 0, 1, 2, so on m plus n. Now we can also write down the PMF of x and PMF of y. The Px of x going to be m choose x, p power x 1 minus p power m minus x for x belongs to support of x. And py of y going to be n choose y, p power y 1 minus p power n minus 5 for y belongs to support of 5. Okay, fine. Now let's write down the PMF of x plus y using a convolution formula. Fine. Now the PMF of x plus y using the convolution formula for t belongs to support of x plus y. The px plus y of t going to be what? Summation x runs over support of x, right? What is support of x? 0, 1, 2, so on. So the px plus y of t equal to summation x equal 0 to m px of x times py of t minus x. This is the convolution formula. Okay. Now let us use the PMF of x and PMF of y here. Okay. The px of x I am writing m choose x p power x 1 minus p power m minus x. Py of t minus x I am writing n choose t minus x p power t minus x 1 minus p power n minus of t minus x. Okay. Now in every term this p power x and p power t minus x get multiplied and simplified to p power t, and also this 1 minus p power m minus x and 1 minus p power n minus of t minus x get multiplied and simplified to 1 minus p power m plus n minus t. Okay, in every term this is what happens. Okay, in every term we have this p power t 1 minus p power n plus n minus t. So we can take that one common. So we end up with this p power t times 1 minus p power n plus n minus t times the summation. Okay, summation x equal 0 to m choose x times n choose t minus x. Now using Vandermon's identity, this summation we can write m plus n choose t. Okay, because of Vandermon's identity. Now we have px plus y of t equal to m plus n choose t p power t 1 minus p power n plus n minus t. Now this you can recognize as PMF of binomial distribution with the parameters m plus n comma p. So we can say that this x plus y follows binomial distribution with the parameters m plus n comma p. Fine. Now we are going to study probability distributions of transformations in RK. We have already studied probability distributions of transformations in R. That is, when we have a y equal to g of x, where g is the differentiable one-to-one transformation from the support of x to support of y, then we know the PDF of y in terms of PDF of x is fx of g inverse y of modulus of the Jacobian of the transformation d of g inverse y by dy for y belongs to support of y, right? Okay, now let me write this way. Here the transformation y equal to g of x, if you solve for x, what we have x equal to g inverse y, right? Let me call this one h of y. Okay, now we can also write this derivative of g inverse y with respect to y as like a dx by dy. So in these terms, the PDF of y I can write fx of h of y modulus of dx by dy. Here this dx by dy is Jacobian of the transformation. Okay. Now we are going to generalize this idea to k-dimensional random vector. Okay. Okay. Here is the theorem. Here let x under bar is a k-dimensional random vector x1, x2, xk with a joint PDF fx under bar and the support sx under bar. And we have transformations yi equal to gi of x1, x2, xk for I equal to 1 to k, which maps sx under bar to sy under bar, which is a one-to-one transformation, so that we have a unique solution for these equations. Okay, so these equations yi equal to gi of x1, x2, xk can be uniquely solved for x's like this: xi equal to hi of y1, y2, yk for I equal to 1 to k. We also assume that these gi's have a continuous partial derivatives, and The Jacobian of the transformation is denoted by dou of x1 x2 xk by dou of y1 y2 yk, which is the determinant of this k by k matrix. Here the ijth entry of k by k matrix is dou xi by dou yj. Okay, ijth entry is dou xi by dou yj. Determinant of this k by k matrix is called Jacobian of this transformation, which is denoted by dou of x1 x2 xk by dou of y1 y2 yk, which should be non-zero. Okay, now under these assumptions, joint PDF of y under bar going to be, okay, where y under bar is the k dimensional random vector y1 y2 yk. The joint PDF of y under bar at y1 y2 yk equal to fx under bar of h1 of y1 y2 yk. This is nothing but x1, and h2 of y1 y2 yk. This is nothing but x2. So on hk of y1 y2 yk, this is nothing but xk times modulus of the Jacobian of the transformation, that is modulus of dou of x1 x2 xk by dou of y1 y2 yk for y1 y2 yk belongs to support of y under bar. This is how we are going to get the joint PDF of y under bar in terms of joint PDF of x under bar and the Jacobian of the transformation. Okay, fine. And we are not going to prove it here because this directly follow from the change of variable technique that you know from multivariable calculus. If you know what is the change of variable technique, it should be obvious. Okay, fine. And it looks similar to what I wrote in earlier for univariate case, that is the PDF of y is fx of h of y times modulus of dx by dy. Okay, so this is generalization to k dimensional random vector. If you take k equal to 1, this one will reduce to this one. Fine. Okay, fine. Example, let xy be bivariate random variable with a joint PDF of xy. These are our transformations. U equal to x plus y, v equal to x minus y. You think like a u equal to g1 of xy and v equal to g2 of xy, where g1 of xy is x plus y, g2 of xy is x minus y. These are going to be one-to-one transformations, and they are going to have continuous partial derivatives. Okay, so these equations u equal to x plus y, v equal to x minus y can be solved for x and y like this. X will be equal to u plus v by 2, y will be equal to u minus v by 2. Okay, now we can look at the Jacobian here, dou of xy by dou of uv. Okay, so what is this? Determinant of this 2 by 2 matrix. What are the entries here? The 1 entry going to be dou x by dou u, 1 entry going to be dou x by dou v, 2 entry going to be dou y by dou u, 2 entry going to be dou y by dou v. So what is the dou x by dou u? As you can see, it is going to be 1 by 2, and dou x by dou v also 1 by 2, and dou y by dou u also going to be 1 by 2, and dou y by dou v will be equal to minus 1 by 2. So that's why the data of this matrix is going to be again minus 1 by 2. Okay, so fine. So the Jacobian of this transformation going to be minus 1 by 2. Now the joint PDF of uv in terms of joint PDF of xy. Okay, now this is like a h1 of uv. Think like this is like a h2 of uv. Okay, so how do you write this one? Fu of uv is going to be fxy of h1 of uv comma h2 of uv. What is h1 of uv? U plus v by 2. h2 of uv is u minus v by 2 times modulus of the Jacobian. Okay, modulus of the Jacobian. So this is going to be mod minus 1 by 2 going to be 1 by 2. So now let me clear this. Now we can write like this. Joint PDF of uv going to be 1 by 2 times fxy of u plus v by 2 u minus v by 2. Okay, this is the joint PDF of uv in terms of joint PDF of xy. For example, if I take x and y are independent exponential random variable with the parameters lambda 1, lambda 2 respectively, then the joint PDF going to be product of marginal PDF. So the joint PDF of xy I can write fx of x times fi of y. What would be fx of x? Lambda 1 times e power minus lambda 1 x. Fi of y going to be lambda 2 times e power minus lambda 2 y for x positive and y positive. So joint PDF of xy going to be lambda 1 lambda 2 e power minus lambda 1 x minus lambda 2 y for x positive, y positive, 0 otherwise. This is going to be joint PDF of xy. Now the joint PDF of UV is going to be what? 1 by 2, this 1 by 2 times fxy of u plus v by 2 u minus v by 2. Here simply replace x with a u plus v by 2, y with a u minus v by 2. So we have of here lambda 1 lambda 2 e power minus lambda 1 u plus v by 2 minus lambda 2 u minus v by 2. Here x is what? U plus v by 2 positive, u minus v positive. Okay. Now this can be further simplified. Okay, so we can write of lambda 1 lambda 2, if I take u common and v common like this, minus of lambda 1 plus lambda 2 of u plus lambda 1 minus lambda 2 of v. Okay, so this is equivalent to u plus v positive, u minus v positive. This is the support of UV. Okay, fine. Okay, this is how we can get the joint PDF of UV in terms of joint PDF of XY. Here the joint PDF of XY happen to be lambda 1 lambda 2 e power minus lambda 1 x minus lambda 2 y for x positive, y positive, 0 otherwise. Fine. Okay. Bank post office problem. Say you got a work in bank as well as in post office. Now you are in the bank standing in a queue and you are the 8th customer to be served in the bank. That means there are a minus 1 customers ahead of you. Let me assume that average number of customers that are served in the bank is lambda. Okay. If I let x denote the your waiting time to be served in the bank, the next follows the gamma distribution with the parameters a comma lambda, because these customer services happen under Poisson process with rate parameter as average number of customers that are served in the bank per unit time. Okay, and your waiting time is going to be time taken to serve 8th customer, which is going to follow Erlang distribution with the parameters a comma lambda. And we know that Erlang distribution is special case of the gamma distribution. So let me say that x follows the gamma distribution with the parameters a comma lambda. Once you got served in the bank, then you go to post office. Now you are in the post office standing in a queue and you are the bth customer to be served in the post office. That means there are b minus 1 customers ahead of you. Let me assume that average number of customers that are served in the post office, again same parameter lambda. Okay, if I let y denote the your waiting time to be served in the post office, then y follows the gamma distribution with the parameters b comma lambda. Okay, for similar reasons. Okay, now let t denote the total time you spent in the bank and post office, that is t equal to x plus y, and let w denote the proportion of the time you spent in the bank, that is w equal to x by x plus y. Here you can see that x and y are independent because this waiting time in the bank should be independent of waiting time in the post office. So x and y must be independent random variables. Now we can see that this t actually follows gamma distribution with the parameters a plus b comma lambda, because we already know sum of independent gamma random variables with the same rate parameter going to be again gamma random variable. So I can say that this t equal to x plus y follows again gamma distribution with the parameters a plus b comma lambda. But we can't say anything about w yet. Okay, so our goal is going to be get the PDF of this w, which is the proportion of the time you spent in the bank. Okay, fine. Here the support of t going to be interval 0 to infinity, because what is t? T equal to x plus y, and x and y are gamma random variables. So the support of x going to be interval 0 to infinity, support of y going to be interval 0 to infinity. So obviously support of x plus y must be again interval 0 to infinity. And the support of w going to be interval 0, 1, because for x positive, y positive, x by x plus y value always between 0 and 1. So that's why the support of w must be interval 0, 1. Fine? Okay. Now, the transformations t equal to x plus y, w equal to x by x plus y can be uniquely solved for x and y like this. X equal to wt, y equal to 1 minus w times t. Here, x plus y equal to t, right? If you plug t here, after cross multiplication, you will have x equal to wt. If you plug in wt here, then y is going to be t minus wt, that is y equal to 1 minus w times t. Okay, so we have x equal to wt, y equal to 1 minus w times t. If you think like this one is g1 of xy, this one is g2 of xy. Okay, this wt going to be h1 of tw, this 1 minus w times t going to be h2 of tw. Okay, fine. Now, let us compute the Jacobian for this transformation. Jacobian of this transformation is denoted by dou of xy by dou of tw, which is the determinant of this 2 by 2 matrix. Here, dou x by dou t, w, dou x by dou w, t, that you can see from this. Dou y by dou t, 1 minus w, dou y by dou w minus t, that you can see from this. If you compute the determinant of this 2 by 2 matrix, you will have w times minus t minus 1 minus w times t. This is going to be minus wt minus t plus wt. So these two cancel, you will have minus t. So the Jacobian of this transformation is minus t. Fine? Okay. We already realized that x and y are independent random variables because waiting time in the bank should be independent of waiting time in the post office. So the joint PDF of x and y we can actually find like this. PDF of x and PDF of y. Here x follows gamma distribution with the parameters a comma lambda. So the PDF of x, fx of x should be lambda times lambda x to the power of a minus 1 e power minus lambda x by gamma a, and y follows the gamma distribution with the parameters b comma lambda. So the PDF of y, fy of y should be lambda times lambda y to the power of b minus 1 e power minus lambda y by gamma b. Okay, so this is going to be giant PDF of x and y. Further, this can be simplified to lambda to the power of a plus b, because here we have lambda to the power of a minus 1, here we have lambda to the power of b minus 1. Total gets multiplied to lambda to the power of a plus b, and we have x to the power of a minus 1, y to the power of b minus 1, and e power minus lambda of x plus y by gamma a times gamma b. Of course, this is for x positive, y positive, 0 otherwise, right? So the joint PDF of xy that we got is this, okay? Now let us write down the joint PDF of TW in terms of joint PDF of xy and the Jacobian of the transformation, okay? So now the joint PDF of TW, ftw of tw equal to fxy of wt comma 1 minus w times t times modulus of the Jacobian for t positive and 0 less than w less than 1. Here this wt is like a h1 of t comma w, that is x. Okay, this 1 minus w times t is like a h2 of t comma w, that is y. Okay, now Jacobian we already computed, that is minus t. Okay, now to get this fxy of wt comma 1 minus w times t, what we do, let us simply substitute wt for x 1 minus w times t for y in the joint PDF of xy. Okay, let's do that here. Lambda to the power of a plus b and wt to the power of a minus 1, 1 minus w times t to the power of b minus 1, e power minus lambda t. Here wt plus 1 minus w times t going to be equal to t. That's why this e power minus lambda of wt plus 1 minus w times t going to be e power minus lambda t. That is the e power minus lambda t. And modulus of the Jacobian is minus t, right? So mod minus t by gamma a times gamma b. Okay, so this is going to be equal to t because t positive. Now here let me multiply and divide by gamma a plus b. Okay, now let me rewrite the joint PDF of TW like this. Let me separate T things and W things like this. Lambda to the power of a plus b. Here we have a t to the power of a minus 1. Here we have a t to the power of b minus 1. Here we have a t. The total is t to the power of a plus b minus 1. So we have t to the power of a plus b minus 1 and e power minus lambda t by gamma a plus b. And we have a w to the power of a minus 1, 1 minus w to the power of b minus 1 by gamma a times gamma b by gamma a plus b. This is nothing but beta ab. Okay, fine. Let me clear this. Now the giant PDF of TW I am writing like this. Okay, lambda times, so this one I am writing as lambda times lambda t to the power of a plus b minus 1 e power minus lambda t by gamma a plus b times w to the power of a minus 1, 1 minus w to the power of b minus 1 by beta ab, right? Where the beta ab is beta function that you know. Okay, fine. Now we already know about t. T follows gamma distribution with the parameters a plus b comma lambda. So the PDF of t should be lambda times lambda t to the power of a plus b minus 1 e power minus lambda t by gamma a plus b for t positive. So if you integrate this PDF over its support, that is 0 to infinity, then you should get the value 1, right? Okay, so that's why this integral value must be equal to 1. Okay, now to get the PDF of W, what we do? We integrate the joint PDF of TW with respect to T. Okay, so this is how we get PDF of W from the joint PDF of TW. Here we are integrating joint PDF of TW with respect to T. Here T limits are 0 to infinity. Fine. When we are integrating with respect to t, things involving only w going to be constant, right? So this whole thing we can bring out of the integration like this. Okay, now we end up integrating only this part. Okay, but this value is going to be 1 from the start, right? Because this is actually PDF of the t, which is a gamma distribution with the parameters a plus b comma lambda. Okay, now so the PDF of W, FW of W going to be W to the power of A minus 1, 1 minus W to the power of B minus 1 by beta AB. Okay, so therefore the PDF of W we can write W to the power of A minus 1 times 1 minus W to the power of B minus 1 by beta AB for W between 0 and 1, 0 otherwise. Here this W is said to have something called beta distribution with the parameters A and B. Okay, as you can see, the proportion of the time you spent in the bank actually follows something called beta distribution with the parameters A and B. Okay, here is the notation. We read it as W follows beta distribution with the parameters A comma B. Here you can see the graphs of PDFs of beta distribution for various parameter values of A and B. And also we can see that joint PDF of TW actually product of PDF of T times PDF of W. Therefore, T and W are independent. This is interesting. We don't see this fact with our intuition. Yet the total time is spent in the bank and post office and the proportion of the time is spent in the bank actually independent. It's hard to see with our intuition, right? Fine. Okay. Now, we worked with a PDF of this beta distribution in assignment 3. We derived expectation and variance for this beta distribution already. We are again going to derive expectation and variance for this beta distribution using some interesting approach. Okay, fine. Now we are going to find the expectation of W and variance of W, where W is a beta random variable with the parameters A and B. First of all, here X follows the gamma distribution with the parameters A comma lambda. So I can say expectation of X A by lambda, okay, and expectation of X square, actually I can write variance of X plus expectation of X whole square, and variance of gamma random variable with the parameters A and lambda going to be A by lambda square. This is A by lambda whole square. Okay, fine. T also follows the gamma distribution with the parameters A plus B comma lambda. So I can write expectation of T equal to A plus B by lambda, and expectation of T square, again it's going to be what? Variance of T plus expectation of T whole square. So variance of T going to be A plus B by lambda square. This one is A plus B by lambda whole square. Okay. Now here W is X by X plus Y, right? That means I can write X by T. So I can write X equal to TW. Okay. Now expectation of W, I can write expectation of X by expectation of T, because X equal to TW, right? So expectation of X going to be expectation of TW, and T and W are independent. So this expectation of TW, I can write expectation of T times expectation of W. So if I bring this expectation of T this side, so I can write expectation of W equal to expectation of X by expectation of T. But we already have expectation of X equal to A by lambda and expectation of T equal to A plus B by lambda. So the expectation of W going to be A by lambda by A plus B by lambda, lambda lambda cancel. So expectation of W going to be A by A plus B. Okay, so expectation of beta random variable with the parameters A and B is A by A plus B. Fine. Okay. Next, let us find out the variance of W. We compute variance of W using this formula: expectation W square minus expectation W whole square. Expectation W we already got, that is A by A plus B. So this is going to be A by A plus B whole square. Now this expectation of W square, I can write expectation X square by expectation T square, because X equal to TW, right? That implies X square equal to T square W square. So expectation X square equal to expectation T square W square, but T and W are independent random variables. So this expectation T square W square will be same as expectation T square times expectation W square. Now if I bring this expectation T square this side, I can write expectation W square equal to expectation X square by expectation T square. So this expectation W square I wrote as expectation X square by expectation T square. In the previous slide, I wrote expectation X square equal to A by lambda square plus A by lambda whole square, and expectation T square equal to A plus B by lambda square plus A plus B by lambda whole square. Okay. Now this expectation X square I can write as A by lambda square plus A square by lambda square from this. This expectation t square I can write as a plus b by lambda square plus a plus b whole square by lambda square from this. Okay. Now this expectation w whole square I can write as a square by a plus b whole square. Now this whole thing gets simplified to ab by a plus b whole square times a plus b plus 1. Feel free to verify this. Okay. So therefore the variance of w going to be ab by a plus b whole square times a plus b plus 1. Fine. Here is an example involving transformations in R3. Let x1, x2, x3 are independent random variables and each xi follows exponential distribution with a parameter 1. That is the PDF of xi at xi going to be e power minus xi for xi positive 0 for xi less than or equal 0. Okay, for I equal to 1, 2, 3. Okay. Now here x1, x2, x3 independent, so the joint PDF of x1, x2, x3 must be product of its marginal PDF, that is PDF of x1, x2, x3 at x1, x2, x3 going to be fx1 of x1 times fx2 of x2 times fx3 of x3. So this should be equal to e power minus x1 times e power minus x2 times e power minus x3 for xi positive for I equal to 1, 2, 3, 0 otherwise. Okay. So the joint PDF of x1, x2, x3 should be at x1, x2, x3 e power minus of x1 plus x2 plus x3 for x1 positive, x2 positive, x3 positive, 0 otherwise. Okay. Fine. Okay. Now let me consider these transformations. y1 equal to x1 plus x2 plus x3, y2 equal to x1 plus x2 by x1 plus x2 plus x3, y3 equal to x1 by x1 plus x2. We can see that support of xi going to be interval 0 to infinity for I equal to 1, 2, 3 as xi's are exponential random variables. So the support of x1 plus x2 plus x3 also going to be interval 0 to infinity. Okay, the support of y1 is going to be interval 0 to infinity. But the support of y2, support of y3 going to be interval 0, 1 because this x1 plus x2 by x1 plus x2 plus x3 value always between 0 and 1. Similarly, this x1 by x1 plus x2 value also between 0 and 1 always. So that's why I can say the support of y2 will be interval 0, 1. Support of y3 also interval 0, 1. Fine. Okay. Now these transformations y1 equal to x1 plus x2 plus x3, y2 equal to x1 plus x2 by x1 plus x2 plus x3 and y3 equal to x1 by x1 plus x2 can be uniquely solved for x1, x2, x3 in terms of y1, y2, y3 like this. Okay, here if you multiply y1, y2, y3, what happens? This one cancel, this one cancel. So x1 equal to you will get y1, y2, y3, that is x1. Again from this one, the denominator x1 plus x2 plus x3, if I see as a y1, then x1 plus x2 going to be y1, y2. So we already got x1, y1, y2, y3, that implies x2 I can write y1, y2 minus y1, y2, y3. That means I can write y1, y2 times 1 minus y3, that is going to be x2. Now we have x1 and x2. Okay, anyway, now we want x3. So x3 going to be from this y1 minus of x1 plus x2. That x1 plus x2 again from this I can see as y1, y2. So x3 going to be y1 minus y1, y2. So I can write y1 of 1 minus y2. So we have x1 equal to y1, y2, y3, x2 equal to y1, y2 times 1 minus y3, and x3 equal to y1 times 1 minus y2. Fine? Okay. Now let us find out the Jacobian for this transformation. Okay. Jacobian of this transformation is denoted by dou of x1, x2, x3 by dou of y1, y2, y3, which is the determinant of this 3 by 3 matrix. Here the ijth entry of 3 by 3 matrix is dou xi by dou yj. Okay, here dou x1 by dou y1 going to be y2 y3, dou x1 by dou y2 going to be y1 by 3, dou x1 by dou y3 going to be y1 by 2, that you can see from this. Okay, similarly these entries going to be these entries. Okay, now if you compute the determinant of this 3 by 3 matrix, you will end up with minus y1 square y2. Feel free to verify this. Okay, fine. Now we got the Jacobian of this transformation. Okay, now let us write down the giant PDF of y1 y2 y3. Okay, now the giant PDF of y1, y2, y3 in terms of giant PDF of x1, x2, x3 and the Jacobian of the transformation that we computed, it's going to be this. The giant PDF of y1, y2, y3 at y1, y2, y3 equal to giant PDF of x1, x2, x3 at y1, y2, y3, comma y1, y2 times 1 minus y3, comma y1 times 1 minus y2 times the modulus of the Jacobian. Okay, for y1 greater than 0, 0 less than y2 less than 1, 0 less than y3 less than 1. Okay, fine. And the Jacobian that we got is minus y1 square y2. Okay, so this is going to be equal to y1 square y2 because y1 positive, y2 positive. So modulus of the minus y1 square y2 going to be y1 square y2. Now to see this, what we do, we substitute y1, y2, y3 for x1, y1, y2 times 1 minus y3 for x2, y1 times 1 minus y2 for x3 in the giant PDF of x1, x2, x3. Okay, this is what we get. Okay, here this is the modulus of the Jacobian y1 square y2 times e power minus x1 plus x2 plus x3. So e power minus of y1, y2, y3 plus y1, y2 times 1 minus y3 plus y1 times 1 minus y2. Here we have y1, y2, y3 plus, this is going to be y1, y2 minus y1, y2, y3 plus y1 minus y1, y2. Okay, as you can see, this one cancel, this one cancel. So we have e power minus y1. So the giant PDF of y1, y2, y3 at y1, y2, y3 equal to y1 square y2 times e power minus y1 for y1 positive, 0 less than y2 less than 1, 0 less than y3 less than 1, 0 otherwise. This is the giant PDF of y1, y2, y3. Fine. Okay. We have not seen any methods to find out the PDF of some function of given continuous bivariate random variable. That is, let us say you have a random variable u which is a function of xy, g of xy, where xy is continuous bivariate random variable with a joint PDF of xy. Here u is going to be univariate random variable which is a function of xy. We have not seen any methods to find out the PDF of u for some general function g of xy. The only method that we have seen is convolution formula that will work only for g of xy equal to x plus y, that too when x and y are independent. These are the limitations for convolution formula. Okay. Now we are going to give a powerful method using transformation, using which we can find out the PDF of u for some general function of g of xy, provided g having continuous partial derivatives. Okay. Okay. Here xy is the continuous bivariate random variable with a giant PDF of xy, u equal to g of xy. If we are interested in finding the PDF of u, then we can do the following. First we take u equal to g of xy as the one transformation. Now introduce another auxiliary transformation v equal to h of xy, so that this mapping is 1 to 1. xy to g of xy comma h of xy should be 1 to 1 mapping. Then we can find out the giant PDF of uv in terms of giant PDF of xy and the Jacobian of this transformation. Okay, once we get hold of this giant PDF of uv, then we can find out the PDF of u like this. Okay, integrating the joint PDF of UV with respect to V from minus infinity to infinity. This is how we can get the PDF of U. Okay, this is the method. Fine. Note here, we may have a lot of choices for V equal to H of X5, but to make the problem easy, the simplest choice would be V equal to X or V equal to Y. Let's do one problem using this method. Okay. Problem. Let X and Y are two independent standard normal random variables. Then find the PDF of U equal to X by Y. Here X and Y are standard normal random variables. So the PDF of X I can write 1 by root 2 pi e power minus x square by 2 for minus infinity less than x less than infinity. The PDF of Y 1 by root 2 pi e power minus y square by 2 for minus infinity less than y less than infinity. And here x and y are independent, so the joint PDF of x is going to be PDF of x times PDF of y. So the product of these two PDFs is going to be 1 by 2 pi times e power minus of x square plus y square for minus infinity less than x less than infinity minus infinity less than y less than infinity. Okay, and here our transformation u equal to x by y, and we take an auxiliary transformation v equal to y. Okay, fine. Now these transformations u equal to x by y, v equal to y can be solved for x and y uniquely like this. X equal to uv, y equal to v. Because here y equal to v, right? So if you put v here, if you cross multiply, then you get x equal to uv. Obviously, y we have a v. So we have x equal to uv, y equal to v. Okay. Now let us compute the Jacobian for this transformation. Jacobian of this transformation is denoted by dou of xy by dou of uv, which is the data of this 2 by 2 matrix. Dou x by dou u going to be v, dou x by dou v going to be u, that you can see from this. Dou y by dou u going to be 0, dou y by dou v going to be 1, that you can see from this. Okay, data of this 2 by 2 matrix will be v. The Jacobian of this transformation is v. Fine. Okay. Now let us write down the giant PDF of uv in terms of giant PDF of xy and the Jacobian of this transformation. Okay. Now the giant PDF of uv at uv equal to giant PDF of xy at uv comma v times modulus of the Jacobian for minus infinity less than uv less than infinity and minus infinity less than v less than infinity. Actually, this will cover all plane. So in the next step, I can write minus infinity less than u less than infinity minus infinity less than v less than infinity. Okay, fine. Here the Jacobian we got is v, right? So this is going to be mod v. Now to see this, so we have to substitute uv for x, v for y in the joint PDF of xy, that is 1 by 2 pi e power minus 1 by 2 of x square plus y square, that is for minus infinity less than x less than infinity minus infinity less than y less than infinity. Fine. Okay. Now the giant PDF of uv at uv going to be 1 by 2 pi e power minus 1 by 2 of u square v square plus v square times mod v. Okay. Modulus of the Jacobian going to be mod v. Fine. For minus infinity less than u less than infinity and minus infinity less than v less than infinity. Okay. So now we got the giant PDF of uv. Now let us find out the PDF of u. Okay. Now to get the PDF of u, we have to integrate the giant PDF of uv with respect to v from minus infinity to infinity. What is the giant PDF of uv that we got? 1 by 2 pi e power minus 1 by 2 of u square v square plus v square times mod v for minus infinity less than u less than infinity, minus infinity less than v less than infinity. Okay, so that's why we have to integrate this giant PDF 1 by 2 pi e power minus 1 by 2 of u square plus 1 v square. Here we are taking v square common times mod v dv. Now you can see that here we are integrating with respect to v, and this integrand is even function of v. So this integral I can write 2 times integral of 0 to infinity v. Here mod v I can write v because from 0 to infinity mod v will be v. So integral 0 to infinity v e power minus 1 by 2 of u square plus 1 v square dv. Okay. Now let us take the substitution t equal to v square, then 2v dv equal to dt. Here this 2v dv will be dt. Okay. Again t limits also will be 0 to infinity. So this integral going to be 1 by 2 by integral 0 to infinity e power minus 1 by 2 of u square plus 1 t dt. Okay. Now this integral with respect to t. Now this integral going to be e power minus 1 by 2 of u square plus 1 t by minus 1 by 2 of u square plus 1. Okay. So your limits are 0 to infinity. So it's going to be 1 by 2 pi limit t tends to infinity e power minus 1 by 2 of u square plus 1 t by minus 1 by 2 of u square plus 1 minus e power 0, that is 1 minus 1 by 2 of u square plus 1. Okay. Here this u square plus 1 is positive. Okay. As t go to infinity, this will go to 0. So this will be 0. And minus minus here plus. So we end up with this. So the 2 to cancel. So you will end up with a 1 by pi times 1 by u square plus 1 for minus infinity less than u less than infinity. Okay. Therefore, the PDF of u that we got 1 by pi times 1 by u square plus 1 for minus infinity less than u less than infinity. As you can see, this u equal to x by follows Cauchy distribution. That means the ratio of two standard normal random variables follows Cauchy distribution. Fine? Okay. Let me stop now. Thank you.